Hi everyone, Dr. P here, and in this lecture we'll go ahead and take a look at Hess's law. Now, one of the things to remember about enthalpy, H, is that it's a state function. So that means delta H is pathway independent. It only matters where we start and stop. So it doesn't matter if a reaction is one step or multiple steps. For example, we could have the following reaction: N2 gas plus 2O2 gas react to give 2NO2 gas, and our delta H equals 68 kilojoules. We'll call that delta H1. Or what if we wrote N2 gas plus O2 gas reacts to give 2NO gas, delta H, we'll call it delta H2, so delta H for this reaction is 180 kilojoules. And then a second reaction is 2NO gas plus O2 gas reacts to give 2NO2 gas, delta H3 equals minus 112 kilojoules. So I could go ahead and add these chemical reactions, because remember, these are chemical equations. So I can add my equations and things will still be equal. And then I add the delta H's. So what we end up getting then is N2 gas plus O2 gas plus 2NO gas plus O2 gas react to give 2NO gas plus 2NO2 gas, and then delta H2 plus delta H3 equals 180 kilojoules plus minus 112 kilojoules. So overall, let's see, I can collect my two O2s, my two NOs cancel, so these guys cancel out. So I have N2 gas plus 2O2 gas reacts to give 2NO2 gas, and delta H equals 180 minus 112, which is 68 kilojoules, which is what we said up here. Okay, so we can, if for example we have a reaction that is maybe difficult to measure in a calorimeter, but we have two steps that maybe are individually easier to measure, we can go ahead and measure things that way. And I'll do an example in just a minute. Some things to note here: if we reverse a reaction, the sign of delta H is also changed. And then the magnitude of delta H is directly proportional to the quantities of the reactants and products. So it's as written. So if I had to multiply through one of the equations by 2, I'd have to multiply the delta H by 2. So again, why do we bother with this? Well, we can write a one-step reaction for a multi-step one, because we measure delta H of the individual steps, it's easier, and then we put them all together for the overall reaction. So let's take a look then at another example here. And let me grab a piece of paper here. So let's say we had carbon, that is graphite, that's solid, and it's reacting to form carbon diamond, that is solid. Delta H equals question mark. Now, I have a question mark here because this would be very difficult to measure. Trying to perform this reaction, if you try to turn graphite into carbon at a laboratory scale, it requires immense temperature and pressure. In the for naturally occurring diamond, it requires immense pressure, high temperature, not as high as, say, the synthetic diamond, but more pressure and a lot more time. So measuring this would be very difficult. But we can measure each of the following reactions. So let's look at our first reaction. We'll take graphite and we'll treat it with oxygen and we'll blow it up. We'll burn it. So we'll do this in our bomb calorimeter. We can measure that delta H for reaction 1 is minus 394 kilojoules. And now reaction 2, we can have diamond, and we'll blow that up in our bomb calorimeter, or burn it in our bomb calorimeter, and we'll get CO2 gas. And delta H here, delta H2 equals minus 396 kilojoules. So let's take reaction 1 and then minus reaction 2. So we're going to reverse reaction 2. So let me write these out again here. C graphite solid plus O2 gas goes to CO2 gas. Delta H1 equals minus 394 kilojoules. And then CO2 gas goes to C diamond solid plus O2 gas. So minus delta H2, because we reverse the reaction, that's going to be plus positive 396 kilojoules. So now if I add these up, I will get C graphite solid plus O2 gas plus CO2 gas, react to give CO2 gas plus C diamond solid plus O2 gas. And now my O2 gases cancel and my CO2 gases cancel. So I'm left with graphite going to diamond. And then if I add my delta H1 and my minus delta H2, I end up getting delta H equals 2 kilojoules. And that's 2 kilojoules per mole of reaction as written. So I really should say 2 kilojoules per mole. And what I mean by mole of reaction, well, it means if I write it this way, I'm saying 1 mole of graphite, 1 mole of diamond, etc. So you can see here how we could get an actual value that we couldn't otherwise measure, but we get it because of Hess's law. We can measure other reactions and then mathematically reverse one reaction and add it to the other, and we can come up with getting a delta H for an otherwise difficult to measure reaction. All right. So in the next lecture video, we'll go ahead and we'll look at some other uses of enthalpy, and also we'll make use of Hess's law again, but in a more fundamental way with standard enthalpies of formation. All right, well, thanks for watching, and in the meantime, stay safe out there. Bye now.